This is a lesson on functions and their graphs in a course on Precalculus. I want to start with just an introduction about what functions are. What are functions? To distinguish them from relations, where relations are a set of ordered pairs, but functions have very specific rules about that relation that exists. And that is that each input leads to exactly one output. I have this example down here from the OpenStax Precalculus text, second edition, and it shows each of these is a relation, but some of these relations is a function, and this one on the end is not a function because what happens is if you put in an input value, there is two output values. That's not allowed with a function. I'll get into graphs and how that appears on a graph, but that is the definition of a function is each input results in one output. And two inputs can have a single output value, that's fine, but you can't have an input that results in two outputs. That's not allowed. That happens more frequently with formula. Identifying functions. So as we look at learning objectives for this lesson and the unit overall, you need to be able to identify functions, and you need to be able to represent functions with words, tables, and graphs, as well as the proper function notation. So a proper function notation, the proper symbolic representation is called function notation or functional notation. I call it function notation. Is symbolically representing an output in the form of an equation. And remember that equations have equal signs in them. 2m plus 5 is an expression, not an equation. If I want to make this into a function, I would have to say that the function of m equals 2m plus 5. So you can see that's how I articulated this. Typically we use x and y. I used m over here, but typically we use x and y. And we'll say that y is a function of x. And what students, when they first learn this, they think this is f times x. That's not what it is. What this means is that there is a function, and the input variable is x, and the output is y. Okay, so we're talking about independent variables and dependent variables. We'll get into x and y axes and how to read that on x and y axes. A few examples that I use in physics is maybe velocity is a function of time. Height is a function of time. I do pressure is a function of volume. Maybe a magnetic field is a function of the radius away from a wire. So when we look at these, for me, it's not just x and y. There's so many variables that we can use, and when we look at real life contexts, we're going to have different variables. And so when I pick these variables, there's typically standard input variables. T is time, h is height, position, x. All right, it's not P for position, it's X as a location on an axis, which is different than P for pressure, okay? There's an example down here I pulled from the OpenStax text. Use function notation to express the weight of a pig in pounds as a function of its age in days. So when I look at this, it says as a function of. So when I read this, remember words mean things, and when I see this phrase as a function of, so that's what I've said before. Magnetic field is a function of radius. So whatever it says as a function of, this will be the input variable. So if you get confused about which variable goes where, they'll say as a function of. That will be your input or x variable. So I know that I'm going to have a function of days, and let's see, we have a weight of a pig. We might call that W. So I have weight as a function of days. So that's proper function notation. I will expect you to use it. Typically what I see students do in homework assignments is they'll just write 2m plus 5 and think they're done with that. But proper function notation includes an equal sign and this out front, f of m. Pressure is a function of volume. You'd have nkt over v. This would be the whole function, not just one part or the other, but the two things combined. So keep that straight while you're doing problems and when you're writing out your work. We get into evaluating a function. This is probably review in the way that output values can be calculated numerically given a numerical input. You've probably done this in prior classes. If I take and put, let's say, f, I have this function up here. It's a function of a line. F of, let's go 0. Easy, right? F of 0, if I plug 0 in, that just means wherever I see x, I'm going to put in 0. So there's x negative 3 times 0 plus 5. Well, I'm going to get a plus 5, and that's f of 0. As you move forward in this class, I'm going to be emphasizing algebraic expressions and representing things in terms of variables. So you can see that's what the examples of that I have here. F of 3x, that means wherever I see x in the original equation, I'm going to put in the expression 3x. So f of 3x, just doing the work here, I'm going to get negative 3 times 3x plus 5. Wherever I see x, I'm going to put in that expression 3x. Okay, so what is that? Negative 9x plus 5, and that would be the answer. Okay, this is different. You notice that there's a 3 in here. That's different than 3 times f of x. 3 times f of x is going to be 3 times negative 3x plus 5. I'm going to distribute, use my simplification. I get negative 9x plus 15. These are two different values, two different expressions here, right? So watch where you do your evaluations, what you plug into the equation, and operations that you do on this. I would call this 3 a scaling factor. That's what I would call it. I'm a physicist by nature, and in mathematics I find a lot of times I'll just call it a scaling factor. Just multiply it by 3, it makes it 3 times larger, right? Which is different than making the input 3 times larger. This is making the output 3 times larger. All right, so if I do the next one, just quickly going through these, f of x plus 3, I'm just going to take the same thing, negative 3x plus 5, that's the original function, and add on 3. So negative 3x plus 8. That's different than plugging in x plus 3. So wherever I see x in there, I'm going to put in that whole expression x plus 3. Negative 3x plus 3 plus 5. Notice wherever I see x, I plugged in that expression. So what do I get? Negative 3x minus 4, right? That's a minus 9 plus 5 is a minus 4. F of negative x, I'm going to plug in wherever I see x, I'm going to put in negative x. We can see that this switches the sign on that first term, plus 5. That's different, again, than multiplying the function by negative 1 itself. I'd take the negative of negative 3x plus 5, and that'll give me 3x minus 5. Okay, so those are pretty simple examples. As we go through the course, I will be throwing harder and harder evaluative functions at you, and that is intended to sharpen your college algebra skills, and you will need these as you move forward, especially in science applications. Evaluate a function at expressions. I wanted to go through here. I have a little bit harder expression here. And what I'm going to highlight is that you may feel the need to simplify these. I did on the prior slide. I simplified them. H of 5x, I can see h of x is this expression. So h of 5x, wherever I see x, I'm going to put in 5x instead. 5x squared minus 3 times 5x minus 9. And I do believe if you enter that into my open math, that's it. You may feel compelled to simplify it further, which is fine. That would be the simplified version. But as you see, these expressions become more complicated and more complicated. Taking the time to do that algebra, can take some time, and you have to watch out for errors. You will continue to make errors. Even the best people make errors when you're doing this stuff. But to simplify in general, I can just do this. X plus 5 squared minus 3, x plus 5 minus 9. Done. That's it. Same thing down here. 2x minus 4 squared minus 3 times 2x minus 4 minus 9. Done. That's all that takes. Okay. There will be situations, and we'll see them during this lecture, where we will need to simplify. But that's it for just evaluating algebraic expressions. You can simplify it from here, but that's the simple first plug this in. Okay. I'm going to move on to the rest of this lecture is going to focus on graphical representation of functions. A graph is a very important tool to mathematicians and to scientists in general. You will not get away from graphical representations. My experiences with students is some really like algebra and forget to do the graph, and some students always do the graph and have no clue how to do the algebra, and you need to know how to do both. You cannot do one or the other. So as we move through this class, I'm going to emphasize this correlation of there is a representation of the algebraic expression equation of a function, and there is a corresponding graph. And notice that I do call this a representation. Okay, it's a representation. It's a way to represent the relationship between the input and output variables. So when we think about a graph, and this should be review, on the horizontal axis, this is the horizontal, right? Horizontal. This is represents the input variable, and the vertical axis represents the output variable. Typically, this is x and y, but in my previous examples, I might have time versus height. I might have pressure versus volume. All right, so when you read your function notation, I have height as a function of time. Remember, this is the input, or the output goes first, and the input goes in the parentheses. And so that's how you read that on a graph. For me in this class, you'll be expected to know that. For me in physics, if you move forward with me in physics, you will be expected to know that. This is convention. I know sometimes it doesn't make sense, because when I read a graph, they'll say plot height versus time. And you think height goes here and time goes here, but that's not how it goes. It's height versus time. They always say the output variable versus the input variable. Why do we like graphs? Because the shape allows us to make generalizations and characteristics on the relationship that become apparent when we represent the information. Our eyes, our brains have, through millions of years of evolution, developed to help us notice things, right? And so when we read a graph, it will allow us to see things on a graph that we would not apparently see in the algebraic equation of that function. Okay, we can see how it curves, we can see how it peaks, and we can see how it changes over time. We would be able to see intercepts, right? There'd be intercepts on there. There are a lot of things on a graph that are very important features. So when I say important features, these are the things that I'm talking about that become apparent on a graph that's not in that algebraic equation. A lot of times, why? To see whether there is a relationship between variables. So especially as we move towards regression, is there a relationship between two variables? What does that relationship look like? This is not a linear relationship, and we'd be able to identify it very clearly with our eyes, as opposed to like if we just had a graph. Or I'm sorry, if we just had a table of values, it'd be hard to decide whether it was a linear or maybe it was just a really flat parabolic. Once we graph it, we'd be able to see a line or a curve otherwise. And it often makes relationships easier to understand. As we move through this course and you look at choosing functions for yourselves to study, you will be using graphs, and a graph will make that relationship easier to see as you're looking at data. Graphs of functions. When we look at functions in particular, and this is what I was talking about a little bit earlier, when I have an input, a single input, so like when I look at -2 on this graph, it has a single output. And we call that the vertical line test. I can see for any value of x, there's 1, -1, -1, and 1, 2. Each one of these values has a single output value. For each input, there is a single output. There could be 2 outputs that are the same value. For instance, if I look at a parabola on a graph, right? If I look at 2, it's going to have, or -2 here, it's going to have the same output value as 5.5. -2 has a single output, and -5.5 has a single output. Okay, so when I take a vertical line and I move it across that graph, for each x value, that vertical line intercepts the graph at only 1 point. There's only one output for each input. So we can see that number 9 here, that is a function. I can represent x, y as a function of x in here. That is a function. When I look at 10 over here, and let me get rid of my example. When I look at 10 here and I run a vertical line across here, when I get to 2, let's just look at 2. I have a vertical line. I can see that 2 here has 2 output variables. This is not a function, not a function. Okay, because for an input variable, I get 2 outputs. Not allowed. Number 11, what do you think about number 11? Function or not a function? I do believe it is a function. For each vertical line that I run across here, I get 1 output variable. So I am going to say that is a function. We can get more particular about functions. One-to-one functions are a special type of function that pass a horizontal line test. So instead of going vertically across, we'll go horizontally up and down, right? So when I look at number 9 here, and I'll get a different color so we can look at it, I'm going to run a horizontal line across there as best I can. And I can see that for this horizontal line, there's 3 values of x for a value of y. That does not pass the one-to-one function. When I do this over for the other function that we've identified, if I run a horizontal line across here, 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 this is a one-to-one function. So this is a function. This is a one-to-one function. You may see that as you move through the material. A particular thing about graphs, it allows us to identify a domain and range. Domain and range, and this is often reviewed for people at this point. Domain is all real input or x values or horizontal values that would not cause us to attempt to find an undefined mathematical operation. It's all the allowed values of x. What are the allowed values of x for this graph? Okay. Can be determined. How can I determine this? Listing the input values as a set of ordered pairs. Identifying the input values of a function written as an equation, or inspecting the graph of a function. I often just defer to number 3. You will need to be able to do this algebraically and graphically, right? So graphically is number 3 up there. Algebraically, do I think that's 1 and 2? Maybe it's 2 written as an equation. Yeah, number 2 is algebraically. Then just graph this as well. It can be easy to see on a graph what the range is. And that's the advantage of graphs, right? It allows us to see things visually that would be hard to determine algebraically. Okay. Again, you would need to figure out the range algebraically, but you can use the graph to verify your algebra. I wanted to do a quick review about domain and range notation, where we're using interval notation. You can use inequality notation, but often when we're doing this, we prefer interval notation. And this is just a reminder of how to do interval notation. This isn't a graph, it's a line graph, I guess. It's not a full like Cartesian 2D graph. It's just a line graph. So when I look at this, I have values between 5 and 10. And notice that I have an open dot at 5, so the function cannot equal 5. But it can equal 10 down here. There's a closed dot down there. So when I do this with inequality notation, what I'm going to say is 5 is less than x, which is less than or equal to 10. Okay, right? It can equal 10, but it can't equal 5. What does this look like in interval notation? Well, remember interval notation, it looks like 2 points. It looks like a point. But what happens is that on the end we have brackets, and we have parentheses. And a parenthesis means that it can't equal that value, so it can't equal 5. And always remember that it goes from lowest value to highest value. I see students switch those values, and that's not the way to do it. The convention is always to go from least to high. So 5 to 10, and because it can equal 10, I'm going to put a bracket, a square bracket on the end there. So that's how I would do that in interval notation. I have a few more examples here just to keep practicing. Let me get rid of this. So we switched it around. Now it can equal 5 and it can't equal 10. So we'll go 5 less than or equal to x less than 10. And I would just change those around. It can equal 5, but it can't equal 10. So I get a square bracket next to the 5 and a parenthesis next to the 10. Okay. We have can't equal 5 or 10. So 5 less than or equal to x less than x less than 10. So when I write this out, and again, this is when it looks like a point, but that's okay. We're going to note that we know it's interval notation, so we know to read this as an interval, not as a 0.5, 10 on a graph. I have a few more here. I do believe we're going to get to infinity. How do I represent when a graph goes infinitely in one direction or infinitely in the other direction? It could be infinitely high or infinitely low. And so remember on this side, there's a negative infinity over on this side and a plus infinity over on that side. So when I see this arrow going to negative infinity, I'm going to say that the low end is negative infinity. And note that a value infinity is not actually a number. So we're going to say that it's not equal to. All right, it's not equal to. I'm just going to put a less than there, less than or equal, and then it looks like that it can't equal 10 either. So that's how I would represent it in inequality notation. In interval notation, I'm definitely going to put a parenthesis here, cannot equal negative infinity, and then it says that it cannot equal 10. So I get parentheses on both sides. Couple more here. Maybe try this one on your own. What do you think that will be in interval notation? In interval notation. In inequality notation, I'm just going to say x is greater than or equal to 10. It can be any value beyond that. Some students in this will not be marked correct. I'm going to put it here. This is the wrong way to do it. Wrong. 10 less than or equal to x less than infinity. That is the wrong way to do it. You do not want to do it that way. That is wrong. We're going to make just one statement that value can be greater than 10, greater than or equal to 10. I have to include both the values when I do interval notation. So this was what you have in your head. Did you get it correct? On the bottom end, I have 10 and it can be equal to it. On the top end, I have infinity and we cannot equal infinity, so we get a parenthesis on that end. The last question here. What's going on here? goes to negative infinity on one end, it goes to infinity on the other end. It can equal all of the values. So how we represent that in inequality notation, we're going to say it's a double bar R. This is all real numbers. It can equal all real numbers. That's what this represents here. That symbol there with a double bar R, it means all real numbers. It goes from negative infinity to positive infinity. When I write this in interval notation, I'm going to have a negative infinity on one end, a positive infinity on the other, and it can't equal those values, so I get parentheses enclosing them. So you'll be expected to know how to write both inequality notation and interval notation for domains and ranges. So let's practice this with graphs. We have some graphs going on here, and I'm going to remind you that the domain represents all of the input variables that are possible, and the range represents the output variables on the vertical. So the red and green here. Notice that we have some signs going on. I have a dot there and I have an infinity here. Okay. So when I look at x values, it starts at negative 5. So if I say domain, it starts at negative 5 and it goes all the way up. It looks like it keeps going in the x direction. So the other end is infinity. It can never equal infinity, and I notice I have a closed dot on my graph, so the domain is negative 5 to infinity. The range, when I look at the range on the top is 5, and it goes all the way down. It keeps going down, 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 down to negative infinity. So when I think about those two numbers, and this is where I see students make this mistake. This is wrong. All right, here's a wrong example. 5 to negative infinity. What's wrong with that? What's wrong with it is not in order. We always want to go lowest to highest, largest, all right? Lowest number to largest number. So the lowest number is negative infinity, and then it goes up to 5. You can't see that. Let me write it someplace else. Negative infinity up to 5. It can equal 5. It'll never equal negative infinity. So that would be the range for this. So don't write things wrong. If you get something wrong, make sure that's one of your decision tree checks that you do in checking your answer. Go ahead and do this in your head real quick. What is the range and what is the domain for this? As I read this, I can see that there's a clear beginning and a clear ending for this function, whatever this represents. Okay, the domain is the x values. Remember, this is the x values, this is the y values. The x value starts at negative 3 and goes up to 1. It cannot equal negative 3, and it can equal 1. So I get a parenthesis bracket. The range, I can see that it's at 0 twice, but it can't equal 0. In one situation, it can equal 0. And in another situation, it can equal 0. So what I'm going to do here is I'm going to say that it goes from, notice I have to go from high to low too. I need to go from bottom to top when I'm doing range. So I'll go negative 4 to 0. I'm going to put a bracket on negative 4, and I'm going to put a parenthesis on 0. It can equal 0 at this one point. So I'm going to generalize that overall. Let's do a little bit harder example. For domain and range, I picked a much harder function. It says, what is the domain? So we're just doing the domain. We don't have to find the range. We're just doing the domain of this function. Notice that there's a square root in the numerator and a denominator. So we have to figure out what that is. The easiest thing to do here, and this is multiple guess, you'd be able to get the answer correct after 4 or 5 tries. Hopefully the second or third you get it. But show the algebra required to answer this problem, then verify your answer on a graph. So I'm very specific about how I want you to do this, and that's what you might see on an exam, is not just like what's the answer, but show your reasoning behind it. So when I look at this function, there's 2 things I noticed was the numerator and the denominator. I want to take the square root of something that is greater, equal to, or greater than 0. So I can't take the square root of a negative number. So I'm going to say x plus 2 has to be greater than or equal to 0, and that's going to tell me something about what x can equal due to that square root being in my function. The other thing that I need to notice is that x minus 1 cannot equal to 0. It can equal all other values, but if I have a 0 down in the denominator, the function's going to blow up. I can't have that in the denominator. So I'm going to take that expression in the denominator and set it not equal to 0. And so what you're going to see is that x cannot equal 1. X cannot equal 1. That is true for the function. What happens is you'll have either an asymptote or a hole there. That's usually what happens. It results in an asymptote or a hole. I'll talk about more about holes as we get to extraneous solutions in rational and radical functions, all right? If we deal with up front, we have to say that x is greater than or equal to negative 2. Okay, so that gives us our domain. I can have a range of values here, right? X is greater than or equal to negative 2, which seems like I might be able to go negative 2 to infinity like that, right? But what happens is it cannot equal 1, and 1 is within the middle of that range of values, right? Do you see which answer that you want here? Do you want to select one right now? I can label these A, B, C, D, and E. Maybe guess which one you think it is. If I have this 1 in the middle and it can't equal it, I'm going to say that I can have x values from negative 2 to 1, can't equal 1, and then I'm going to combine it with another range of values that starts after 1 and goes up to negative infinity, and I can't have it equal, positive infinity. I can't have it equal to infinity, so I'm going to put a parenthesis there. So our answer to this question is B. Okay, a little bit more complicated. We're going to practice this more as we get to more complicated problems. I have a few of these sprinkled in early in the class, but as you get used to finding restricted values and extraneous solutions, then you'll be able to answer these probably with more proficiency. Let's check this guy out on a graph. It says, show the algebra required to answer the problem, then verify your answer with a graph. So let me do this. I think I popped in here the graph of this guy. Where did I pop it in here? Let's go back here. There it is. I see it. It's hiding. There's the graph. So when we look at this graph, let me move it to the front here, bring the front, and look at this graph. Okay, there's this graph. And I mentioned this word before. You might have seen it on a graph before, but didn't know what was going on. Note that x cannot equal 1. Do you see what's happening at x equals 1? This black dotted line that I have put on the graph, this one here, that is the asymptote x equals 1. And notice that x cannot equal 1 corresponds to an asymptote of x equals 1. So as the function approaches that, you can see that the value never gets to 1. It gets closer and closer and closer and closer, but it never equals it. The other thing that we're going to notice on here is that the x value is greater than or equal to negative 2, and we've identified that on the graph too. Another thing we look at on a graph is average rate of change, and I'm introducing to you the difference quotient today. If you've not seen the difference quotient today, welcome to the difference quotient. It's similar to the average rate of change, and the first place you see average rate of change is actually the slope of a line. M is the change in y over the change in x, right? y2 minus y1 over x2 minus x1. That is what the average rate of change in the difference quotient essentially is you're taking the ratio, the change in the output over the change in the input. Okay, that's what an average rate of change is, and the difference quotient is the same concept. It's the same concept. As we look at this, and I am very aware that we're setting the stage for derivatives. The difference quotient sets the stage for derivatives. As you look at derivatives, you'll take the limit of this as h goes to 0, and you'll get a point, and that's the derivative. So keep that in mind as we move through the course and you're heading towards calculus, and that's why we're having you do this. This is also a point in the course that I use to sharpen your college algebra skills. You can see that we're going to have a subtraction of values on the top. If we're using algebraic expressions, you're going to be doing algebraic simplification on the top, and it can get complicated depending on how complicated your original function is. Okay, an important learning objective for this course is to recognize that the difference quotient, the average rate of change, and the difference quotient represents a secant line between 2 points in the graph. So what do I mean by that? What do I mean by that? Let's pick this point. This is x1, y1. Everybody okay if I say x1, y1? Actually have values. x1 is 0, y1 is 5. At some point down the road, let's choose this one. That's a nice point here. This will be x2, y2, right? It actually has values. x2 is 7 and y2 is 4. Right? And if I wanted to just find the slope of a line that connects those 2 points, right? I'll do the best I can to connect them. There's a line that connects those 2 points. This is what we call a secant line between those 2 points. This graph is not a line. You can see that there is a curve on this graph. This graph is not a line. It is nonlinear. This is a nonlinear graph. Rates of change can tell you if graphs are linear or nonlinear. And so that's what the average rate of change or the difference quotient will find when you calculate them. It'll find the slope of that secant line, right? The average rate of change equals the slope of the secant line. If I put this on an exam, I would expect you to be able to find an average value. I can choose another one. Let's see. Do I have another clear point here? 16. I have an x3, y3, right? Which would be what? 16, 0. I can find the secant line between those 2 points, and forgive me for not having a straight edge here. I'm going to connect them the best I can. Pretend that was straight. The average rate of change would be the slope of that line. Notice the slope of the first line is different than the slope of the second line. And that happens when you have a curvy function. If you have a line, the slope here would be the same as the slope here as the slope here. A line has a constant slope. But if you have a curvy line, that slope changes as your values of x change. Hold on to that as you move to derivatives as well. As you take this limit, as h goes to 0, you end up with a tangent line. And notice a tangent line at any point along here. Notice the tangent line of that slope, the slope of that tangent line also gets steeper over time. That tells us that it's curving downward rather than curving upward. I guess it becomes more negative over time, right? It gets larger in value, but this is a positive upward change, and this is a negative downward change. It gets larger downward as opposed to larger upward. Okay, let's do an example of the difference quotient. You can notice down here, one of the learning objectives I have for you is to efficiently, and accurately, those can both be questionable even for professionals. Efficiently and accurately use average rate of change and the difference quotient in a variety of contexts. Make sure you can do algebra. We're going to do an algebra example here in a second. Graphs, just like I did here, can you find the average rate of change from a graph? And can you use these concepts in contexts and applications in science? That would be a cool thing to do. So let's do an example here real quick of a difference quotient. Find the average rate of change. So for me, like I said on the previous slide, the average rate of change and the difference quotient is the same for me. I'm considering this a difference quotient example because here I don't have just like two numbers. To me, if I find an average rate of change, I'd be finding two numbers. A difference quotient, and it's because I see this h here. That's why I'm identifying it as a difference quotient, is because there's an h in there. Remember on the previous slide here, I had an h. I take my y2, which is evaluating at some larger point by h, subtracting y1, and then I get these two things subtracted, which leaves me an h. So I see that h down in there, and that's why I'm calling this a difference quotient. So what we're going to do in order to find the difference quotient is we're going to take f of 5 plus h, subtract off f of 5, and then we're going to divide by x2 minus x1, so 5 plus h minus 5. So that's average rate of change, difference quotient. You may see how it results in the same equation, right? F of x plus 5. So what I'm going to note here is that I need to figure out f of 5, and I need to figure out f of 5 plus h. If I want f of 5, what I'm going to do is just evaluate this function at 5. Wherever I see x, I'm just going to plug in 5. Squared plus 6 times 5 plus 1. For this down here, for this expression down here, f of 5 plus h, wherever I see x, I'm going to put in 5 plus h squared plus 6, 5 plus h plus 1. So I'm going to evaluate these. 5 squared is 25 times 4 is 100. 6 times 5 is 30, and then I have a plus 1, that's 131. Down here, I'm going to have to do some simplification. And remember I said before, when you evaluate, sometimes you just need to enter this, but because we need to simplify, be sure to simplify as much as possible. We need to be able to simplify this down to a single simplified expression. So I need to multiply all this out. I need to do a FOIL on this one. Remember, this is not just 25 plus h squared, right? I have to do a FOIL, and I get cross term 25 plus 2h plus 2 times 5 times h. So I'm just going to put a 10h here, plus h squared, 10h, plus 30 plus 6h plus 1. One more step of distribution here, 100 plus 40h plus 4h squared plus 30 plus 6h plus 1. Let's do one final simplification. I'm going to put the 4h squared out front. I'm going to go from highest power to lowest power on my h. So I have a 4h squared. I have a 40h and a 6h, so I'm going to plus 46h. And then I have 130 and plus 1, so plus 131, which is a similar number before. So I'm going to take these two values, right? This is represented, it's 131. This expression, I'm going to plug in wherever I see f of 5 plus h. So let's write this all out. 4h squared plus 46h plus 131 minus, right, this is f of 5 plus h, minus 131. That's f of 5. And then I'm going to divide by 5 plus h minus 5, h. Okay, so beautiful things happen that we like. I have a plus 131 here and a minus 131 here. Those two cancel each other out. So I get this intermediate expression in here, 4h squared plus 46h divided by h. And so the difference quotient, or the average rate of change here, is going to be, there's an h on top and an h on the bottom. Remember, that means I need to divide each term by h. write that out for you all. Some people forget. And so I can take that and simplify it one more step here. I'm going to get 4h plus 46. That's the expression and the answer that they're going to want in the box for this problem. That is the most simple version. Is it the most simple version? I suppose you could take a 2 out, 223, right? That might be the most simple version. I think this is adequate in order to answer the question. That's fine for me as a physicist, maybe. Okay, so that's how you do that problem. I see students struggle with that, but like I said in the previous, efficiently and accurately. That took a few minutes to do with all those details. So please be as detail-oriented the first time you do this problem, and that will help you not have to spend more time trying to find your mistakes on it. So this is working with the algebraic version of the average rate of change or the difference quotient. But when we look at rates of change in graphs, there's a few things that we look at in regard to, is it increasing or decreasing? And also, I mentioned this before, is it linear or nonlinear? So what we do is we look at the slope of a tangent line. I mentioned the slope of a tangent line. At every point along this curve, there is a tangent line at that point. And notice that the slope of that tangent line is changing. As I look at the increasing portion of this, right, the tangent line becomes less steep. As it's decreasing, it becomes more steep. Okay? A function is increasing when the rate of change is positive, and it's decreasing when the rate of change is negative. And it's definitely nonlinear because this tangent line is changing slope. The slope of the tangent line here is steeper than the slope of the tangent line here, so that's how we know it's nonlinear. So you'll get some questions about that, you'll see. Behavior of graphs, there's some other behaviors of graphs that I want to cover after average rate of change here. Zeros, when you look at graphs, and I had mentioned this before, zeros are very important points on a graph. Not only would you be required to identify and algebraically solve for the x-intercepts, right? These are the intercepts. Zeros are intercepts. We're going to have x-intercepts, and we're also going to have a y-intercept. Remember that because we have functions, there's only going to be one y-intercept. There can be multiple x's, but there's only one y. We would be looking at the domain and range. We already talked about domain and range. Local minima and maxima, I'll get to that in a second. To me, that relates to domain and range because when I look at the domain and range, the maxima and minima, and words mean things. You probably know what maxima and minima means. There's a minimum here, an absolute minimum. There's another minimum here, and there's a maximum right here. Do you all see that? There's maxima here. There's absolute maxima and absolute minima, and there's local maximums and local minimums. We can see regions where it's increasing or decreasing. We can figure out if it's concave up or concave down. We can figure out end behavior. End behavior is what's happening at the ends of this function in symmetry. So let me cover these ones that I haven't gotten to yet. Minima and maxima, again, to me, the meaning is in the word. The highest and lowest points, minima and maxima, highest and lowest points. I mentioned these words before. The local maximum or the local minimum is within a region. Has an output value smaller than the output values in neighboring ones. So when I looked at the graph before, there was two minimum. One was a local minimum and one was an absolute minimum. So absolute is the max or min over the entirety of a function. Okay, let's chat about end behavior. End behavior describes the values y takes on as x goes to large numbers in the negative and positive direction. So what values does y take on as x goes into the end, right? That's why we call it end behavior. As x goes to its ends on negative and positive infinity, what is y doing? What's happening in the vertical direction? This could be a value. When I look at this is an easier example here. As x goes to negative infinity, so this would be the left hand. They might call this the left side value, the left side or left hand limit. We're looking at this part of the graph here. As x goes to infinity, as x keeps increasing, what happens to y? Well, I can see that y keeps going up and up and up and up and keeps going. So I'm going to say that as x goes to negative infinity, f goes to positive infinity. I guess in this situation I have p and t, right? As t goes to negative infinity, then p goes to positive infinity. When I look on the other end, as the t value, as the input value goes to positive infinity, so that's what we're looking at here, is the input goes to positive infinity, what does the output do? Well, the output keeps growing and growing and growing and growing, so the output also goes to positive infinity. So that's how you think about that. It could be a situation where, let me draw a graph here, where I might have a function that has some sort of decay and it might go to 0, but it never actually reaches 0. All right. So I would say as x goes to positive infinity, the function here, f of x, goes to 0. Sometimes it goes to a value. It could be that I move this guy up and it looks like this, right? And that there's some sort of asymptote here. Again, we're talking about asymptotes, where it'll go to that value. For this purple magenta, right, as x goes to positive infinity, then I would say the f of x goes to, I don't know what value that is. We'll just say 2. It can be 2, all right? It goes to 2. It never actually equals 2, but it goes to 2. Let's do a quick example just to confirm your learning. I picked out an example here. Taking a look at it, what is the end behavior of this graph? What's the end behavior of this graph? All right. So we have the first part here is x goes to negative infinity. You're always going to have that. You're always going to identify the left range and the right range. As x goes to negative infinity, what's happening with the function? As x goes to positive infinity, I'm doing a little bit of walking around here, what happens to the function? If I label these A, B, C, and D, go ahead and guess which one you think it is. Which one do you think it is? There's some interpretation to do. Part of this class is getting you used to the notation. This arrow notation, as x goes to negative infinity, y is going to positive infinity. So let's see, it can't be A and it can't be C, right? Because those have negative infinity. It can't be negative infinity. As x goes to positive infinity on the right hand side, I see that y goes to negative infinity. So it can't be this one and it can't be this one. So I have narrowed it down to classic B. Okay, that would be your answer on this one. The last thing we're going to discuss on behavior of graphs is symmetry. Symmetry is a test. You're expected to know it. It seems like it might be this odd sort of, why are we studying this feature of a graph? It turns out as you move towards calculus with derivatives, and actually particularly integrals, when you start doing integrals around axes, it's important to notice if I have some symmetry. I'm not going to do a whole calculation. I can just do half a calculation and multiply by 2. All right. So symmetry allows us to see some of that, like how can I make my math easier on a function later down the road. So I'm establishing these seeds now, and the strict definition of symmetry is not like, does it look symmetrical, yes or no. There's a mathematical, technical definition, and it's when I plug in negative x, what happens? All right. Does the function of negative x equal negative f of x? Okay. If it does, then it's odd. Conversely, if f of negative x equals f of x, that's when you get even. No matter, even if I put a negative sign in, I'm going to get the same function out. So it may be that this may feel like you just want to look at a graph and say, is it symmetric in some way? But what you need to do, and you can see I put the equations here for a couple of examples, you need to do this test here. You need to do this proof of proving whether it's odd or proving whether it's even, or actually if neither of these are true, if neither of these tests are true, it could be a neither function. It could be neither even or odd. We're used to things being even or odd. With the case of symmetry, it could be neither. There could be no symmetry on a graph. Even means symmetry around the y-axis. You can see that. Even is symmetric across the y-axis. Odd is symmetric across the x and y axis. So if I flip it over one axis and then over again, then that would be an odd function. If it looks exactly the same when I do that, if I take the graph and I just flip it like this over the y-axis and it's the same graph, it just looks exactly the same, that is an even graph. If I take it and I flip it over the x-axis and then over the y-axis, if I flip it horizontally and then vertically again, and I get the same picture back, then that is an odd function. And if neither of those happens, you have a neither function. It's neither even or odd. Okay, so there's an algebraic test and there's a graphical test that you can do to figure out even and odd. You're expected to know both of these. So, for example, find f of x. So we did this already. Evaluate the function. We get 4 times negative x to the 4th plus 2 times negative x to the 3rd plus 3. Well, when I plug this in and simplify it, I get 4x to the 4th minus 2x cubed plus 3. And so I compare this thing, I compare it to the original function. And so if I take negative f of x, I get negative 4x to the 4th minus 2x cubed minus 3. If this equaled this, then it would be odd. If this equaled the original function, it would be even. So what do you think this function is? Even, odd, or neither? We're going to say it's neither because I have this negative sign here, which says that it's not even. I have a negative sign. I don't have a negative sign here, which means that it's not odd. So this means that this function is neither. Right here, I have this function. There it is. So here's the graph of this function, and let's look at it real quick. I'm going to bring it to the front, and we're going to look at this real quick. There's this function. And when I look at it, notice that it kind of looks like it's even. If I take this function, I flip it horizontally, so that what's on the right will be on the left, and what was on the left is now on the right. It kind of looks like it could be even, but there's this asymmetry down here. Notice there's the asymmetry down here. And it's not odd. An odd function would be if I flip it that way and then I flip it over the x-axis. If I flip it over the y-axis, that's even. If I flip it one more time, that's odd. And then I would get a downward pointing thing, and that's nowhere the original. So this is a neither function. Okay. When I look at this other graph here, it says determine if the function is even, odd, or neither. Here's the function, and they give us the graph. Just looking at the graph, I can tell that it's not an even function. There's no symmetry about that y-axis. It's not the same. If there was symmetry, it'd look something like this. Whatever was going on the x would also be going on the y. It looks like it could be odd because if I do that and then I flip it over one more time, it looks like it would be this. If I take this thing and flip it this way and then flip it this way, I get that thing, right? So it looks like it could be odd, but it needs to be symmetrical around the origin here, okay? If I take it and I flip it, I have 1, 4. Well, that means 1, 4 on the original graph. That means I would need 4, 1 on the other side of it. Do I have a 4, 1 on the other side? Or a negative 4, sorry, negative 4, negative 1, right? I'm flipping it this way and this way. I get a negative on both of those. Do I have a negative 4, negative 1? No, I don't. So there's not symmetry around the origin for this function. We can do the f of negative x. If I plug it in and do this algebraically, I get negative 1 over x plus 3. So we're going to notice that that's not equal to the original function, which had a positive out front. So it's not even, which we already knew from looking at the graph. And then it's not odd either, because negative f of x equals negative 1 over x minus 3, and that's not the case for when I evaluate negative x either. So it can't be odd and it can't be even, so this is a neither case as well. So hopefully that gives you some tools to be able to evaluate both with algebra. Make sure you're showing your work on your algebra and doing all that accurately to prove even or odd or neither, and looking at that graph that can give you the feel whether it's even, odd, or neither.